You have the possibility to solve the exercises. I hope. Do you have the folder that I shared with you? Can you open it?
Yes.
Okay. Well, so the first part will be a bit of theory. Actually, maybe it will be the only theoretical part of the course, or one of the few. Okay, let me check. So yesterday I told you that Monte Carlo algorithms are based on generation of random numbers, of random samples, and they are used to solve very different problems, from simulation of stochastic processes to optimizing to solving integrals and so on. And the first part is to introduce a bit the theoretical framework of Monte Carlo. That will be all the exercises that we will solve are based on this framework and all the nice mathematical properties that this framework has. So let's stay very abstract now. Then this abstract framework will be declinated in all the different exercises that we will see. And let's consider we have a system that is composed of states. X is the state of my system and omega is the state space. And you can imagine this as something super general. And for example, it can be a configuration of the Ising model. So this X contains all the information of the spins up and down of the Ising model. Or it can be an outcome of a game. Maybe you are playing poker and X is the card that you have in the hand or the card that you choose to play. And I'm doing with this parallelism with poker and with the gamblings also in general because Monte Carlo is called Monte Carlo because in the 40s, actually the first techniques of this kind were introduced in particle physics. But then people realized that you can apply these also to gambling programs, to simulate gambling programs. And Monte Carlo there is a famous casino in Monte Carlo, so this is the reason why it's called Monte Carlo. So this is our system. And our system is also described by a probability distribution over our state space. So you can imagine that if you are playing a card game, this is just the probability of extracting a card, or in the case of Ising model, it can be the Boltzmann distribution of the state space. So this is very general. And when you study this kind of systems, you are very often interested in observables over the system. So this is a function of the state, and again, this is very abstract, but for example, it can be the magnetization of your spin system. It can be if you win or lose the game. It's a function of the outcome that you have, that you are observing. And since this system is probabilistic, you are very often interested in the expected value of the observable. And the expected value, you all know it's this formula. Actually here, there is another dependency mix. continuous. Okay, so a summation if your system is discrete, like is in system, and a continuous is if your system is continuous. Your variables are continuous variables. So are you familiar with this formula? I think, yeah, it's like, for example, the ensemble, this is the ensemble average of the magnetization, so this is the average magnetization. Okay, so what happens very often is that your system is very complex. Your state space is huge, for example. In case of Ising, I mean, the size of your state space goes like 2 power n. So each spin can be up or down, so the total number of configuration that you can have is this huge number. So very often solving this summation or this integral is impossible analytically, and very difficult also to implement a computer program to solve it. So Monte Carlo is taught to solve this summation and these integrals. And the idea is the following. So what we know, so let's describe what is Monte Carlo. Let's assume that we know how to generate samples from our state space, which is meaning generating an x from pair ux. So this is meaning that I can do this operation a lot of times, and my computer program is able to give me outcomes that follow this probability distribution. Right? So basically, this is also saying that the number of times in which my random samples are equal to x divided by the total number of samples that I generated is equal to the probability. So this is called a generation of a sample, and in the limit of infinite number of generated samples, the frequencies of my sample are exactly equal to the probability. Alright? So let's assume that we are able to do this. We will see how to do this also in practice. And if we know how to do this, let's assume that we are able to generate a lot of samples, and what I have is a string of samples that we call, for example, like this, that is x1, xn. So we are generating n samples, which are a lot. And what we are doing now with this huge string of samples is to compute what is called sample average. And our sample average is nothing else than this summation. So, I mean, all the Monte Carlo programs will work in this way. So we simulate samples from a probability distribution, n large, and then we compute this summation, in which for each sample that I have, I compute A of that sample, and I get this sample average. And why I'm doing this? Because there is a very simple theorem to prove that this number in the limit of n going to infinity is equal to A. That is this A. Right? So again, to tell you again what is the logic of the study, we are interested in computing averages of observables in complex systems. And the process to do this, instead of solving summation or solving integrals, is to use brute force, compute this, which is called sample average, and the sample average will converge in this limit to the object that I'm interested in. Okay? So this is really the general idea, and you will see this formula and this other formula in all the exercises.
What is the other side? A.
This is sort of capital A, I mean, it's just a symbol to denote the sample average.
What is this in meaning? What is this meaning?
I mean, the only meaning of this object is that in the limit of n going to infinity, I'm building this object because it has this property.
That's an average of A or expectation value of A.
Yeah, I mean, in this limit, this object is exactly this other object. I think I can show you now the proof in the case of discrete distribution because it's super simple. And actually, it's very intuitive. I can show you a simple example. It's very intuitive. So, the proof of this limit for discrete systems is the following. So, let's rewrite everything. Okay, this summation can be written in the following way. If our system is discrete, let me write, then I will explain. Okay, basically what I'm doing here, this is for a number. So here I had n samples. For example, I had, I don't know, samples that were 1, minus 1, 1, 1, minus 1. And here what I'm doing is 1 over 5 of A1 plus A minus 1 plus A1. Right? What I'm doing here is just grouping together the A with the same sample. So this is for writing 1 over 5, 3 times A1 plus 2 times A minus 1. Are you convinced with this writing?
Yeah.
But we are done because I can bring n inside. And this is just the frequency of my random samples, which in the limit of large n is converging to 0. And what I get is the A. Okay? Very well, okay. I mean, this is for discrete system. For, you can imagine for continuous system, you can prove this by like tiling your state space in hypercubes and then doing this reasoning in the hypercube and then substituting the summation with the integral. I mean, yes, in the drive folder there is the proof also for continuous system, but I don't think it's so instructive. And there is only one last property of this framework that it's essential for making Monte Carlo working. And the property is the following. Let me check the notation. Okay. The property is that the standard deviation STD of the sample average is proportional always to 1 over square root of n. And this is super important, and I'll tell you why. Can you guess why? So let me tell you. what is the standard deviation of the sample average. So you can imagine that you have a string of samples, you generate this string, you compute the sample average and you get one result. Then you generate another string and you get another result. So basically the standard deviation is how much your results are dispersed, right? So basically the standard deviation is nothing else than the error that I can make in estimating the true average. So basically you can prove that independently of your P of x or the complexity of your system, your standard deviation will always decrease with n. So you are sure that if n is sufficiently large, you will find the true answer with a small error. And this is basically what that makes Monte Carlo working so well. And I mean, the proof of this statement is not difficult. It's in the note that I uploaded in the folder. You can take a look if you want. And that's basically it. Okay. So this concludes the theory. We will have theory on more specific problems. And what we are going to see today is the computation of areas and volumes with this kind of methods. But I need to do a very small parenthesis before. Can I erase the blackboard? Okay, small parenthesis, but maybe I can just tell you with voice. It's about random number generation. Actually, the only tool that we will use in this class is the generation of uniform random numbers. So you know, uniform if the system is discrete, it's just an integer between 0 and n. If it's continuous, it's a number within an interval. But actually, you usually take for granted that in your computer there is a random number generator. But it's something totally non-trivial, because you have to think that your computer is a completely deterministic object. I mean, there are transistors, there are circuits that always it's 0 and 1, and you have to minimize the probability of errors, which is the probability of noise. So you need to generate something that is random in a machine that it's deterministic, and this is a very complex problem to solve. And people in the 50s, I think von Neumann came up with this idea of pseudo-random number generation, and I can show you an example. Actually, there is an example in the folder. I can show you the exercise. Okay, I share the screen here.
You can minimize it.
Okay, sure. Nice solution. I uploaded an exercise. If you have time, if you are curious, you can try to look at it. But the way in which your random numbers are generated is similar to this sort of philosophy. So what it's used, this is the simplest case. I think nowadays nobody is using this case anymore. It's called the linear congruential generator. You can take a look at Wikipedia. And basically, randomness comes from this map. This is you can see it generates an x n plus 1 given an x n. And this mod is just the modulus, is the percentage in your computer. Is the remainder of your division. Yeah. And what is, behind randomness there is a lot of mathematical theory, and I don't know, but if you choose this parameter very carefully, you get a sequence of x1, x2, x3, and so on and so forth that is completely random. And this is due to the chaotic properties of this map. So I think with Jacopo Grilli you will see a bit of chaos. And the idea is that you can generate randomness with chaos. And this is exactly what your map is doing. You see that this is a deterministic object. So there is an intrinsic problem, because if you start from the same initial condition, you will get the same string. So this used to be a problem because maybe some cryptography program is based on random number generation, and if you knew the seed is called, the initial condition of this map, you can predict the randomness, and so maybe you can crack a system. So there is another problem, you have to generate reliable seeds. So this is what you do, for example, in C++ when you generate a seed. And for example, usually nowadays the seed is related to the time of your internal clock of the computer, which is a number that changes changes very, very fastly. So it's always different. It's difficult to predict. But anyway, it's randomness, but it's not true randomness. It's a pseudo-random number generation. But I find this quite interesting because it's not a trivial problem to solve this, to generate randomness from determinism. And yeah, in this exercise you can see that if you choose the parameter very carefully, actually the parameter that I'm going to choose are these huge numbers. You can generate an x, which is a uniform random variable. You see that the counts are more or less uniformly distributed. But anyway, this was just a brief parenthesis. We are taking for granted. I can stop the share screen. We will use the Python random number generation, which is randint for integer numbers, or rand for uniform random numbers. All right. That is it. Okay. Okay, so now we can move to the next part, which is computational areas. And so the problem that we will try to solve is the following. We have, for example, a two-dimensional plane. So you have a plane, and you have a closed line, which is described, for example, by this equation, whatever. For example, for a circle, it will be x squared plus y squared minus l squared equals 0. And you want to compute the area inside this shape, which is f right here. Okay, so the Monte Carlo method, it's super brute force, and what we are doing is the following: we are generating random numbers in this square. Here. So our samples are nothing else. Let's define, how did I call it? I don't know. Let's define U as a random point. which is ux, uy. Okay, so you have two random points. One random point described by this u. Then you have a very long, a large number of these samples, so you can call this un, is u1, un. So tell me now, which is the probability that your random point falls inside your shape? Can you estimate this probability by knowing? Can you try?
The area of the
Exactly. Yes.
of the
Exactly. So the probability that your point is inside this shape is nothing else than the area of the shape divided by the area of the rectangle. With AUF, it's, yes, you understand, it's the area inside the shape, and the area of rectangle is x2 minus x1 times y2 minus y1. But there is also another way to estimate this Pin, which is by looking at your samples and say that the number of points inside divided by the total number, it will converge to Pin. And so you put together these two expressions and you get the area of your functions is the area of the rectangle times of, let's call it n in divided by n. Okay, and this is a very brute force method to compute the area. Okay, this is for 2 dimensions, but you can imagine that you can extend this for whatever dimension, so it will become a volume. So you increase the dimension, it's meaning that you have more variables inside your function. So for example, you have f of x1, xd, but the procedure is exactly the same. You generate a uniform random number, u1, ud. So for each dimension, you are bounding your shape inside an hypercube, and you have to generate random samples inside your hypercubes. But you have the same, ingredients here, because you can count the number of points that falls inside your shape, which is the point that satisfies this equation. So you can compute n, you know n, you know the area of your hypercube because it's just an extension of the area of the cube, and you can compute the volume, the hypervolume of your object. So that's very simple. And the exercise that you are supposed to solve today is based on this idea. Actually, it's not a direct computation of an area. It's about pi estimate, and I will show you also a video before doing the exercise because it was super. I discovered this video during lunchtime and it was very funny, so I will show you. And the exercise is the following. So you have a square, you have a circle inside the square. This is r, this is of course 2r. You want to estimate pi using Monte Carlo. So basically what I'm doing is, I know that the area of the circle divided by the area of the square is, or the area of the circle is pi r square divided by 2r square. So this is pi over 4. But I know that this object is, again, I generate random numbers inside the square. So again, is n in over n in the limit of n large. So basically I can estimate pi as 4 times, because I have to move this 4 on the other side of the equation. Divided by n. Okay, is that clear? So I mean, I found a video on YouTube in which there were people trying to estimate pi by throwing darts on a. Let me show you. It's only 15 seconds. No. Okay, this is.
I'm here today calculating pi with darts, with the help of
I
variables.
mean, all the points here, I mean,
So the I square is 1, that means
all the points that they have to be enough bad in throwing the darts, so that they are able to generate in a uniform random fashion all the throw. But they are actually this is exactly what I showed you. They discovered that they were too good, so actually they had to
what it looks like. That is to avoid her trying to aim at anything, so we're going to put this on the fence.
I mean, all this point was trying to make it randomly, and at the end they were able to compute pi. I mean, they found 3.13. But yeah, I mean, you can do it also by hand, but it's much faster if you do it with a computer. And yeah, so you can open the exercise, I think. So inside the folder pi estimate, there is exercise pi estimate. And I mean, yeah, I think I can give you half an hour to try to solve the exercise. You can call me anytime, and at the end I will show my solution. And I don't know, maybe I can even pause the recording, because yeah, maybe I can.